let's talk about term symbols and then finding electronic states, so beyond configurations. So first we'll start off with atomic term symbols. So keep in mind these are for free atoms. We don't yet have, for example, a ligand field. So we don't have, we're just talking about an atom of one element or of any certain atomic or electron configuration. So, but no symmetry involved yet because we just have free kind of atoms floating around. So hopefully you remember from general chemistry that for each atom we have quantum numbers. So quantum numbers, numbers, okay, quantum numbers, and of course they are, we have n, our principal quantum number, and of course this is what, like, you know, 1s, 2s, 2p, so it's a 1, 2, 3, 4, ... So this is the which shell you're in. Okay, and then of course we have L, our orbital angular momentum. And this goes from 0, 1, 2, ... all the way up to n minus 1. And remember that this corresponds to what type of orbital that we have. So remember 0 is our s orbital, 1 is our p orbital, 2 is our d orbital, et cetera, et cetera, et cetera. So we have, you know, 1s, and then for when n equals 2, we have 2s, and then 2p, et cetera, et cetera. OK, great. And then now, each electron, when we start populating atomic orbitals, should have its own quantum number. So we have to also think about m sub L, which is the z component of orbital angular momentum. And this is going to be going, m sub L is going to be equal to a range. So this could be minus L plus 1, ... all the way to L minus 1 to L. And this is because, for example, if we think about, let's say, L equals 2, we're going to have 5 d orbitals. So then this is going to be, m sub L is going to be minus 2, minus 1, 0, plus 1, plus 2. Right? So these are the m sub Ls over here. And then so when we have thinking about one electron, it has to have a certain m sub L if it's in an L equal 2 orbital. OK, and then lastly, electrons have spin. So this is the z component of spin angular momentum. And of course, every electron is going to be plus 1/2 or minus 1/2. So m sub s equals plus or minus 1/2. So these quantum numbers, m sub L and m sub s, describe every electron. Remember, by the Pauli exclusion principle, every electron can only have a unique set of quantum numbers. And then once we want to think about the actual atom, then we can have, so let's go on to the actual atom part. Then we're going to have, think about all the electrons within our system. So then we have to think about L, which is the total angular momentum. And then so this is going to be summing across all your electrons. This will be like your m sub L of n. So this is your n electrons. Oh, sorry, I didn't use the word n. I'll use a different variable. Let's say x for x electrons. OK, and so big L, which is the total angular momentum over all electrons, has its own m sub L, big m sub L. And then this is going to, again, vary negative L plus 1, ... L minus 1, L. And then we have total spin, which we talked about before, right? So it's the number of unpaired electrons that you have times 1/2. And then we have also big M sub s, which is going to be negative s plus 1, ... s minus 1 to s. And then together, we have L and s together will also give us j. And then this is going to be equal to L plus s. And this is the total angular momentum. And then this could go from also a range. This will be, well, this we'll talk about later in the context of spin-orbit coupling. OK, so let me quickly erase, and we'll continue on with atomic term symbols. OK, so the atomic term symbol is given as a symbol, obviously. So the symbol itself is expressed usually as, so you have your big L, and then as a superscript to the left, you have 2s plus 1. And then as a subscript, which may or may not always be there, then you might have a j. So remember, so this is our orbital angular momentum, total orbital angular momentum. This is our spin multiplicity. And then again, this is our kind of spin-orbit coupling. Spin-orbit because spin plus orbital, spin-orbit coupling. So each of these numbers together is sufficient to describe a term. And then this term can be figured out once we look at the possible states that we can, possible so-called microstates that we can make out of each electron configuration, which we'll do an example of in a bit. But let me talk first a little bit about this term symbol. So spin multiplicity, let's kind of put it over here. Spin multiplicity. The reason that we show, rather than just showing s, we have 2s plus 1, is because this is the kind of possible ways to arrange this spin. I'll give you an example. So if s equals 0, this is, OK, all our electrons are paired. We have no unpaired electrons, which means that there's only a certain way everything has to be paired. So there's only one way to arrange that in space. So therefore, our spin multiplicity is 2s plus 1. So it's one is singly degenerate. So this is called a singlet state. And if let's say s equals 1/2, this is big S. So our electron could be up or it could be down. And no matter what, we have one unpaired electron. So 2s plus 1 is 2. So this is doublet. So this is our degeneracy because we have two possible spin states, up or down, but they have the exact same total spin, but it's doubly degenerate. That's why it's doublet. And then same if s equals 1, we have two unpaired electrons because 1/2 plus 1/2 equals 1. So they could be both up, they could be down, but they could also be paired. Have three, so because big S has to be able to go from -1, 0 to 1. So that's why 2s plus 1, this is a triplet. And so on and so on. So you can have triplet, quartet, et cetera, just as you go up. So this is the degeneracy, the spin multiplicity. And then similarly, L also has certain degeneracy orbitals. Remember, let's say if you think back to our atomic orbitals, if L equals 2, right, we could have big M sub L is going to be equal to -2, -1, 0, 1, 2. So again, the degeneracy of the multiplicity of L, the orbital multiplicity, is going to be 2L plus 1 is the multiplicity. OK, so our total degeneracy of each term is going to be 2L plus 1, the orbital multiplicity, times 2s plus 1. And then so we'll show in the next video, but this means that this many microstates have to comprise this term. And then, OK, oh, and lastly, sorry, I forgot L is, even though L is a number, we often represent L as a letter. And then so this is just like orbitals. So if L equals 0, 1, 2, then we actually write this as big S. So keep in mind these are capital letters. So this will be S, P, D, let's see, F, G, H, dot, 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 dot. So for example, we might have a state like singlet S. So singlet, 2s plus 1, S. You always read off the 2s plus 1 as this, not as the number. So singlet S, doublet S, et cetera, et cetera. OK, next video, examples.